Up to now, the transformer has been an idea. This part is where it becomes a working system. Because architecture alone doesn't give you benchmark results, the training recipe does. In this section, the authors lay out the exact pipeline that made the transformer both fast to train and strong in performance. The dataset and batching setup, the tokenization choice, the optimization and learning rate schedule, and the regularization tricks that keep training stable. Even if you've never trained a transformer yourself, you'll be able to follow the logic of every choice, because we'll treat each one the same way: the problem it solves, what the paper did, and why it helps. Let's start with what they trained on. For the English to German translation, the authors used the standard WMT 2014 dataset. This consists of about 4.5 million sentence pairs. Each pair is an English sentence with its German translation. For example, "The cat is sleeping," paired with "Die Katze schläft." They used something called byte pair encoding, with a shared vocabulary of about 37,000 tokens. Here's what that means. Instead of treating every unique word as a separate item, which would create massive vocabularies with hundreds of thousands of entries, byte pair encoding breaks words into smaller pieces based on how frequently those pieces occur together. Think of it like reusable word chunks. Common words often stay whole, like the, is, cat. Rare words can get split into pieces and then built back up from those pieces. This keeps the vocabulary manageable while still being able to handle rare words by combining familiar chunks. For the English to French translation, they used the significantly larger WMT 2014 English-French dataset, which consists of 36 million sentence pairs. They split tokens into a 32,000-word-piece vocabulary, essentially the same chunking approach, just with a different vocabulary size. Now, here's an important practical detail about how they organized the training. Sentence pairs were batched together by approximate length. Why does this matter? Imagine you're packing boxes of different heights into a truck. If you mix a 1-foot box with a 10-foot box, you waste a lot of space because you have to make the truck ceiling 10 feet high everywhere. The same thing happens with sentences. If you batch a short 5-word sentence with a long 50-word sentence, you have to pad that short sentence with 45 empty tokens, wasting computation on processing nothing. By grouping similar-length sentences together, they minimized wasted padding and trained more efficiently. Each training batch contained approximately 25,000 source tokens and 25,000 target tokens total. Now, let's talk about the actual training setup. The hardware and timeline. They trained their models on one machine with 8 NVIDIA P100 GPUs. Remember those impressive training times we mentioned earlier? Here are the specifics. For the base models, the standard-sized version, each training step took 0.4 seconds. They ran 100,000 steps for a total training time of 12 hours. For the big models, larger versions with more parameters, each step took 1.0 second. They ran 300,000 steps for a total training time of 3.5 days. Here's why this matters. These training times achieved state-of-the-art translation quality at a fraction of the cost of previous systems. The paper proves this by directly comparing training costs in their results table. 12 hours versus weeks or months. That's the breakthrough. The transformer didn't just match previous results, it got there dramatically faster. Training deep neural networks requires careful optimization. Think of it like descending a mountain in the fog. Deciding how big each step should be matters a lot. The authors use the Atom Optimizer, a popular and effective algorithm that adapts the step size automatically. They used Atom with carefully chosen parameters: beta 1 at 0.9, beta 2 at 0.98, and epsilon at a very small value. But the key innovation is how they varied the learning rate. That's the size of the optimization steps over time. First, what is a learning rate? When training a neural network, you're finding the best values for millions of parameters, the numbers that make up the model. The learning rate controls how much you adjust those parameters after each batch of training examples. If it's too high, you might overshoot the best values and never converge. If it's too low, training takes forever. When it's just right, you make steady progress toward good parameter values. Instead of using a fixed learning rate throughout training, the authors used a two-phase approach. The first phase is warm-up, covering the first 4,000 steps. The learning rate starts low and increases linearly up to a maximum value. Why warm-up? At the start, the model's parameters are randomly initialized. Jumping in with large updates can destabilize everything. Gradually ramping up gives the model a gentler start, letting it find a good initial direction before making aggressive updates. The second phase is gradual decay, which happens after those first 4,000 steps. After the warm-up, the learning rate decreases gradually as training progresses. Why decrease? Early in training, you're far from the optimal parameter values, so you want larger steps to make progress quickly. But as you get closer to the optimum, you want smaller, more careful steps, so the model can fine-tune without overshooting. This warm-up then decay pattern has become very influential. You'll see variations of it in many later models. Now let's talk about preventing overfitting. Deep neural networks have millions of parameters. The transformer has even more. This creates a risk. The model might memorize the training data instead of learning general patterns. Think of it like a student preparing for an exam. Good learning means understanding the concepts so you can solve new problems. Overfitting means memorizing the practice test answers, but failing when the questions change slightly. The authors used several techniques to reduce this risk. The first technique is dropout. This is a simple but effective approach. During training, you randomly turn off some connections in the network on each training step. Why does this help? It prevents the network from relying too heavily on any single pathway. It has to learn more robust representations, multiple ways of recognizing patterns. They applied dropout throughout the network, at multiple key points in the architecture. For the base model, the dropout rate was 10%. The second technique is label smoothing. During training, the model tries to predict the next token. Normally, the target is hard. If the correct answer is cat, you tell the model, cat gets 100% probability, and all other tokens get 0% probability. But the authors used label smoothing at 10%. That means the target is softened. A simple way to picture it: the correct token gets roughly 90% probability, with the remainder spread thinly across the vocabulary. Why intentionally soften the target? It prevents overconfidence. It encourages the model to stay a bit uncertain, which can improve how well it generalizes. The authors note that label smoothing can hurt perplexity. That's a technical measure of how well the model predicts, but it improves accuracy and blue score. These aren't arbitrary decisions. Each choice addresses a specific challenge. Batching by sequence length maximizes computational efficiency. No wasted GPU cycles on padding. Learning rate warm-up prevents early instability when parameters are random. Learning rate decay supports fine-tuning as training progresses. Dropout reduces memorization and improves robustness. Label smoothing reduces overconfidence and improves translation quality. The combination of these techniques, along with the architectural innovations we've discussed in previous parts, is what made it possible to train a deep, attention-based model to high performance in just 12 hours for the base model and 3.5 days for the big model. Think about that for a moment. We've covered 6 parts explaining the architecture: the attention mechanism, the encoder-decoder structure, the feed-forward networks, the positional encodings. All of that is the what. This part is the how. How do you actually make it work in practice? And what's striking is how thoughtful each decision is. The authors didn't just throw a powerful architecture at the problem. They carefully tuned every aspect of the training process, from how they batch sentences, to how they schedule the learning rate, to how they prevent overfitting. That combination of architectural innovation and careful training methodology is what separates a good idea from a working system. Now that we know how they trained it, the natural next question is, how well did it actually perform? How well does the transformer compare to previous systems? And what happens when you remove different components? Which design choices really matter? In Part 8, we'll look at the results. We'll see the proof, the empirical evidence that all these architectural and training choices actually deliver. The translation scores, the comparisons to prior work, the ablation studies that reveal which components are essential and which are nice to have. Because understanding how something works is important, but seeing that it actually works better than what came before, that's what makes the case complete.